Hello. This is video 40. In video 40, I'm continuing the long shopping list of all the different terms for graphs and stuff, but we need another example. Here's another graph example. That's different from the first one. That's why we need another one. At the top, I'm going to put the Arts Center. Arts Center. Oh, this is graph G2, by the way. But you already had that, didn't you? Arts Center, and there's BSC. And here's Dalton Voigt. I'm going to abbreviate DV. Dalton Voigt Hall. And down here is Cowgill. I'll call that Cal in the interest of time. Cal is Cowgill. The entrance on Broadway. Entrance. And over here is the Ghost of Forer Hall. Again, just arbitrary node labels, just so I got a graph I can work with. Now, here's something that's different. Here's an arc between Arts Center and BSC, but that does have an arrowhead. Not only does it have an arrowhead, I'm going to put 20 minutes on there. Maybe the average walking time between the Arts Center and BSC is 20 minutes. You see a lot of your buddies and you stop and talk and ever, but for whatever reason, we do have a label for that arc. From BSC to Cowgill, what have I got here? 15 minutes. Someone is a slow walker. Now then, since this is a directed graph, if we want to be able to move back and forth between two nodes, we will need two arcs, one going each direction. This will be 7 minutes. How could it be 7 minutes that way, 15 the other way? I don't know, I don't care. This is just an example of a graph. Now you might think, well, you can't do that, that's parallel arcs. No, parallel arcs are when you've got two arcs that actually serve the same function. It's almost like having two key values the same in a binary search tree or a red-black tree. If we want to be able to go back and forth, and this is a directed graph, by the way, then we will have to have an arc going each direction, and they're not considered parallel because they do different things. Okay, what else we got? BSC to Dalton Voigt, 15 minutes. Arts Center to Dalton Voigt, 10 minutes. Dalton Voigt to Forer, 10 minutes. What's this? Dalton Voigt to entrance is 5 minutes. Oh, entrance to Cowgill is 8 minutes. And Forer to Cowgill is 1 minute. Hoofing that one. Forer to Cowgill. Is that all the arcs I want? No. Dalton Voigt to Cowgill is 2 minutes. Just gotta squeeze an arrow in here somehow. I need it to match my graph on paper because I've got other examples later on that kind of depend on this. Quick check, is that okay? Yeah. Now over here, I'm going to talk about graph G2. Graph G2, dot, dot, dot. What about it? It is directed. What does it mean for a graph to be directed? It means each one of the arcs is one way. One way. I can go from Dalton Voigt to Forer. In this graph, I cannot go directly from Forer to Dalton Voigt. I might be able to get there going around a path in the graph, but I can't go there following one arc. So it's directed, each arc is one way. It's also weighted. Graph G2 is weighted. What does that mean? It means there are labels on the arcs as well as labels on the nodes. Now in this case they are numbers. The 10, the 10, the 15, the 2, the 5. They don't necessarily have to be. If these had been cities in the US as the labels, then the arc, these directed arcs, they could be the airlines that have direct flight between those two cities. And the airline, you know, even though that would be a weight on the arc, the name of the airline, that is not a number. So it's not necessarily a numerical weight. I like that example. I might have to resurrect that later on. Another thing about graph G2 has an unreachable node. Well, I don't want to, sorry, let me back up. Has a node, this is a better way to state it, has a node that is unreachable from any other node in the graph. There, that's a much better way to state it. And the graph will be assumed. It has a node, graph G2 up here, has a node that is unreachable. I'm just introducing this term, unreachable, from any other node. And you already know who it is, the arc center up here. It only has outgoing arcs. There's no way to get there from any of the other nodes. So if we start off at the arc center, that's okay. We can travel around in the graph. If we start off at the entrance, we can't get there from here. Not according to this graph. That is a phenomenon that can occur in this directed graph. You don't have to think about it real hard to realize if we had a connected, undirected graph, this would not be possible. There would be no unreachable nodes. There would be a path connecting any two nodes. And that's a connected, undirected graph. This one is connected. There are arcs among all the nodes, but there is not a path following the arcs from each node to every other node. Not unless we ignore the directions of the arcs, in which case there is a path. So it's not disconnected components. It's just that there is at least one node here that's unreachable. Now, it could be, this one's universally unreachable by any of the other nodes. It could be that there are, let me see, is there any other node that's not reachable from some other node? I think all the others, looks like there's like a cycle that goes around here. Any of the others, I could start there and then get to any of the others. So that's not a good example for unreachability in general. And a note over here, since I haven't used this space. In a directed graph, comma, adjacency is not symmetric. A, D, J, A, C, E, N, C, Y. Adjacency, one node being adjacent to another node, is not symmetric. If you're familiar with the symmetric property, that just means if A is related to B that way, then B is related to A that way. That doesn't hold in general in a directed graph. For example, BSC and Cowgill, abbreviated, are adjacent to each other, heavily abbreviated. BSC and Cowgill are adjacent to each other. I can follow one arc. I can follow the Cowgill arc to BSC and get there in 7 minutes. I can follow the BSC arc down here to Cowgill and get there in 15 minutes. So those are adjacent to each other, but they're more the exception than the rule here. Over here, Dalton Voigt, I need a but up front of this. But even though Forer, the ghost of Forer, is adjacent to DV, you know where I'm going with this, comma, drum roll, let the drama build a little bit, DV is not adjacent to Forer. Now this is so heavily abbreviated. Indulge me for a second and I'll read this back. See if it makes more sense to me and more sense to you. In a directed graph, adjacency is not symmetric. It doesn't go both ways. BSC and Cowgill are adjacent to each other because there's an arc for each direction. But even though Forer is adjacent to DV, meaning we can get to Forer from DV following one arc, DV is not adjacent to Forer. I can get to DV, I believe. Let me see here. Forer goes to Cowgill, goes to BSC, goes to DV. So there is a path. They're just not adjacent to each other. Is that all I have to say? I'm trying to make sure that I don't get drowned in definitions and terms. I'm trying to focus on just what we need to know for just what we're going to do. And I think that'll do it. 2 examples, G1, G2, and we'll look at more later. I'll see you online.